All right, I chose to do an example of an elastic collision, mainly because there's an important result that's in your perusal videos that I'm having an idea that nobody's bothering to watch. So here's your chance to learn an additional expression that we can use to solve problems where we have an elastic one-dimensional collision. So we have two carts. We put rubber bumpers on them so that they would have an elastic collision. They're coming straight at each other. This is one-dimensional. Cart A is moving to the right with a speed of 0.75 meters per second, and cart B is moving to the left with a speed of 1.3 meters per second. After the collision, they are going to move off in opposite directions. So B is going to move in this direction with its unknown velocity, and cart A is going to move in this direction with its unknown velocity. So this is conservation of momentum in one dimension. And so we have mass A, VA initial, plus mass B, VB initial, equals MA, VA final, plus MB, VB final. I am told the mass of the carts. Cart A is 600 grams, cart B is 750 grams. So I'm going to substitute some values in. Mainly I have things that I know before the collision. So before the collision, I had the mass of A times its velocity initial. And then I multiplied that by the mass of B. And because it was moving to the left, that's why my negative sign is there, because its velocity is minus 1.3. After the collision, I don't know any of the velocities. I'm keeping them as vector quantities, and I will let the signs work themselves out when I do my math. But I did put in the values for the masses. When I do the calculations over on the left-hand side, I get minus 0.525, and this is equal to 0.6 VA final plus 0.75 VB final. Now, this is my one equation I got from conservation of momentum, and you can see I have two unknowns. But when we have an elastic collision, there's another condition, and it talks about the relative velocities before and after. Basically, the relative velocity after, which is taken by subtracting the two final velocities, is equal to minus the relative velocity before. So this is true in all elastic collisions, and this is going to be the condition that we can use. This will give us one more equation that will allow us to solve for both our unknowns. Now we know the initial velocity, so the initial velocity of B was minus 1.3, and the initial velocity of A was 0.75. And so this ends up to be and what we get here is 2.05. So what does this tell me? It tells me that VBF minus VAF, so that's the relative velocities between the two objects after the collision. Like if you measured the speed relative to each other, that's going to be 2.05. What I'm going to do is this can give me an expression that I can substitute in for VB final into my conservation of momentum equation. So I can use this, and I'm going to substitute into here in order to solve for my unknown. So I get minus 0.525 0.25 equals 0.6 VAF plus 0.75 times 2.05 plus VAF. So that's what I've substituted in for VBF. So I get 1.35 VAF plus 1.54. If I rearrange this, I have 2.0 minus 2.065 equals 1.35 VAF. So VAF, that's the vector, ends up to be minus 1.53 meters per second. And VBF, which is just going to be 2.05 plus that value, which is minus 1.53, gives me 0.52 meters per second. So I get these two final velocities. Now, the second question asks, how can I figure out if this was actually an elastic collision, and do your results support this claim? The way that I do this is to see if the initial kinetic energy is equal to the final kinetic energy, because in an elastic collision, kinetic energy is conserved. So I've run out of room here, so I'm going to have to go onto another page in order to do the calculations. So my initial kinetic energy is 1/2 the mass of cart A, which was 0.6, times its initial velocity, which is 0.75 squared, and then 1/2 the mass of the second cart, 0.75, times its velocity, 1.3 squared. It is negative when you square it, it doesn't matter. So I end up with a total kinetic energy of 0.08025 joules. Now let's look at my final kinetic energy. I have 1/2 0.6. Now what we found was the final velocity of A was minus 1.53. We'll square that, and then I have 1/2 the mass of B, which is 0.75, and its final velocity was 0.52 squared. So let's see what we get there. Okay, so when I did this, I got 0.702 plus 0.101, which gives me 0.803, which is basically, I can say within my margin of error that my kinetic energy initial does equal my final kinetic energy. So it is conserved. That is, the kinetic energy is conserved, so this is an elastic collision.